All right, welcome everybody. So this is the first talk of the second week. I'm Mustafa Kalafat, and I'm gonna talk about minimal introduction to minimal surfaces and submanifolds. These are gonna be introductory lectures, and I'm also sharing the notes, and you can able to follow if you repeat it daily. Okay, so today I'm gonna make some introduction. Make some introduction, and we're gonna proceed as much as we can, and starting from curves and surfaces. So the question, so let's start with some natural questions. Natural questions. Natural questions. So what is the shortest path between 2 points in a Riemann manifold? In a Riemann manifold, all right, so that's one of the simplest questions, and the answer is roughly, as you know, geodesics. Like for example, so if you are on the plane or space, a straight line joins these, and if you're on a sphere, for example, plane 3 space, and if you're on a sphere, then so this is two-dimensional sphere. So if you take 2 points, then your geodesic is gonna be maybe it's good if I choose another color for that one. For that one, you can it's gonna be a little bit curvy between these 2 points, P and Q. But in that direction, that's the shortest curve. But if you use another direction, if you prefer to go in the other way around, then you're going to obtain some other curve which is complementary to the first one. Complementary to the first one. the first one. So that so the explanation here is in different directions. In different directions. There are different directions. There is different curves. There are different curves. Here, one of them is globally minimizing, one of them is maximizing. One minimizing the distance. Other maximizing globally. Okay, so if you just think in that direction, okay, it's it is yeah, it is gonna be maximizing. Okay, but of course we would like to think about that great diameter as well, so that to make it into a distance, so that so shortest to make a definition of the shortest path, or to make a intuitive definition for geodesics, you could also count maximizing as well. All right, here we also have some experiment here from the beginning. All right, so what about for the surfaces? What about for the surfaces? What is the so you can ask this question in several different ways. So it is you can ask given a simple closed curve. So what is a surface? With boundary. What is the surface? With boundary on the curve and area minimizing or maximizing. All right, so that's another question. So this is one dimension higher question. So as we can see, the minimizing and maximizing usually comes together, so we're gonna call them. So from basic differential geometry classes, minimal surface, so which is defined as mean curvature. H equals 0. Okay, so just to remind you, so I'm gonna define all these formally, but before than that, just go through them with undergraduate knowledge. So second fundamental diagonalizing. Second fundamental form. So second fundamental form. So it is, if you diagonalize it, it's going to be kappa 1, kappa 2, 0, 0, principal curvatures, and you obtain H to be the sum of these. And remember, your Gaussian curvature is just the determinant of this quantity, remember. Okay, all right. So that's how we define minimal surfaces in the first class, and as in the first class, and here as you can see in tree space, you cannot find a compact example satisfying this. So because of some obvious fact, so remember, if H is 0, if H is equal to 0, so kappa 1 plus kappa 2 is going to be 0, so that kappa 2 is minus kappa 1, and Gaussian curvature kappa equals kappa 1, kappa 2, and that's going to be minus kappa 1 square, so it's going to be negative, non-positive. Okay, negative. Okay, and then it's so that so this implies that no compact example of a minimal surface, compact without boundary, of course, without boundary, minimal surface in the tree space. Okay, so in the Euclidean space, we cannot find the hyperbolic compact hyperbolic surface, so that's roughly a reason, because of negative curvature. But we have positive curvature sphere and zero curvature plane, but it's also or cylinder, but they are not, of course, compact. All right. So to give an example, plane, two plane and catenoid are minimal surfaces, are the only minimal surfaces in R3 obtained as a surface of revolution. Okay, for the plane, you can rotate a line to a point what is a catenoid? So that's let's talk about this a little bit. So so this is a old theorem that I'm not sure you can easily find who proved it. Like this is a subject of 250 years old, as you can see, and that's proved by some classical people. So to make it an example and figure, let's just talk about a little bit catenoid. So this is obtained by rotate the catenary, which is basically cosinus hyperbolic function y equals cosinus hyperbolic x about its directrix, which is the x-axis in this case. All right. So you start with cosinus hyperbolic function. So I'm just going to make it a graph picture. I think it was e to the x plus e to the minus x over 2, if I'm not mistaken, so that passes through 1. And if you rotate it along the x-axis, you're going to obtain a minimal surface with some negative curvature. Also, catenary is the curve obtained by raising a rope, hanging a rope from its two ends. That curve is the catenoid. So somehow it's some critical value of something counted with weight, and its rotation also gives you something similar in terms of surfaces. Okay, so this is the only non-trivial surface of revolution minimal surface in R3. In 3 space. All right, so minimal surfaces are a huge subject developing for 250 years old, and so like I'm just want to make some overall summary of the subject. So I'm just picking up some topics that might be interesting. For example, let me just mention one interesting problem and then pass to our technical proceedings. An important problem in minimal surfaces was the, I hope I didn't miss any slides here. Okay, was the Bernstein problem. Bernstein problem. Bernstein theorem. So he proved some pieces of its problem, of course. So if a surface is given, if So it's first solved in R2, of course. Surface given by a graph R2 to R is minimal, has mean curvature zero if and only if f is linear. Okay, so that's the first stage of a Bernstein problem. So it is actually a theorem which Bernstein proved, and the question was, the problem was is it true in higher dimensions? Okay. So like is it true in higher dimensions for f, of course, from R n minus 1 to R. So its graph of f lies in Rn, and if whether it's mean curvature. So are there any minimal? Are there any minimal submanifolds? Minimal submanifolds other than submanifolds of Rn given by a graph of a function and graph of a function and different than a plane. All right, so that was the general Bernstein problem, and it is like if you look at the literature, it is gonna be so the answer is, you can check the literature. So James Simons and other guys shows you that it is true only plane works for plane for lower dimensions. Counterexamples in dimensions higher. So Simons, etc. So there are many results on this case. Just check the websites if you want to learn further about this Bernstein problem. I'm just picking you up, so that's an interesting subject. Also, there are many problems around minimal surfaces throughout the centuries. Like one of them is, for example, Willmore conjecture, Willmore problem, which is solved in recent years, and giving examples in spheres and so on, and finding indexes. There are many problems, so that today I'm not going to talk about all of them, but just mention some selection here. All right, any questions so far? Okay, so today, how much time we have for tea? maybe we can do half an hour. Okay, so recording continues. All right, so I'm gonna, after giving some motivation and examples, I'm gonna talk about some technical side, so that our reference are gonna be here. We're gonna be mainly use is gonna be Peter Lee's geometric analysis book. So Cambridge University Press, 2012. It is mostly, it includes most of the things we're gonna talk about in this lectures. All right, so our first subject is to prove the first variation of formulas and to understand the minimal surface equations, so that variation of formulas. So we're gonna have several conventions. Convention. For the Riemann curvature tensor, for example, which helps us to compute all curvature quantities, is gonna be, we're gonna using the Lie bracket order. Now x, now y, minus now xy applied to z, and kxy is going to denote the sectional curvature for orthonormal basis, and it is defined through Rxyy convention to make sure xy orthonormal. So this is the sectional curvature. Sectional curvature. And Ricci curvature, we have for Ricci curvature, Rij is going to be the sum, or if you just choose this convention, it is, of course, automatically fits here, so EIEK, but just that we're going to be using it, so just let's write it at the beginning. For an, this is of course holds for an orthonormal basis. E1 through EM. Ricci curvature. Okay, so that's where does this M come from? So let's pick up the dimensions. So you have an, you are in an M manifold and you have an n-dimensional submanifold. Over Riemannian manifold. Manifold MG, and with the induced metric, of course, n, consider n with the and with the restricted or induced metric. From capital M. All right. So that's going to be the spaces we're going to working on, so that we're going to expect capital N to be a minimal submanifold later. So define the tangential component of the covariant derivative in M on N, of course, so that so T is going to be a projection map from the tangent space of M to Tn and nabla T x y is going to be equal to, so you take the covariant derivative inside the outer space and xy in xy are vector fields. XY are vector fields in the bigger space M, and just the notation, if there's a T, you take the covariant derivative and then project onto N, so that wait, oh yeah, right, so XY are vector fields in M passing through capital N, of course. So they are true capital N, but they don't have to be tangent to N. All right, but after this tangential projection, they become. And of course, by this is going to be the covariant derivative inside N. So nabla T is the Levi-Civita connection of n with respect to induced metric from M. From MG. Okay, that's how you obtain the Levi-Civita connection. Remember the natural connection of the submanifold. Here we come close to the minimal submanifolds. So by defining the second fundamental form, is going to be the negative of the normal component. It can be positive also depending on the convention, but here we're going to use the negative convention. So that so negative of so it's going to be the negative of the normal component of nabla. So so if you define what it is, so second fundamental form of x and y is going to be defined to be the negative of the normal component of x and y, y differentiated in the x direction. X direction. So how can you compute this? Of course, you can just write the whole thing and subtract the tangential component, right? So now you write the whole thing and subtract the tangential part and take the negative. Okay, taking the negative depends on your convention. Some people might work with the other one. Remember, for surfaces, we use this this quantity second fundamental form to define minimal surfaces, and we're gonna use the second fundamental form again in the general form to define a minimal submanifold. A minimal submanifold. So here, as you can see, it is a vector field. So here xy. Also, let's mention our domain each time. So where. So here, if you to get the tangential and normal components, you need to be staying on the submanifold. X and y are vector fields on the submanifold. N. But vector fields and it is like they don't have to be the vector field of n only, because they can be they need not to be tangential to n. On our vector fields on the submanifold of n of m. Okay, so in other words, for example, xp for example, at a point at a point n, xp does not have to be in TPN, right? So may not hold. Does not hold in general, of course. But only XP lies in TPM. Okay, just to make you aware of our domain. Right, but here maybe it is yeah, right. So it is maybe this can be defined in general, but we're just going to restrict on TPN. What if you just restrict on TPN? This second fundamental form gives you. Let's talk about that one. So restrict. If you restrict everything inside, as you write it like this, it works for any type of vectors, but we are going to be interested in the vectors tangent to n. And if you restrict that, let's see what's going to happen. Let's see what's going to happen. Thinking as Tn, second fundamental form, just on Tn times Tn. Then after the operation, it's going to be, as I told you, it's going to be going outside Tn. And the result is not going to be inside your submanifold. So it's going to go out of your submanifold. Okay. And the normal bundle, actually. Okay. So this tells you that it's not a closed operation on Tn. Not a. Yeah. It's not a closed operation on Tn. Okay. All right. So if you, for example, let's say if you have a surface and you're in R3 inside R3, if you have two vectors, this is n, so this is m. So you're in R3, so that make a picture that you can see now. So if you have two vectors, for example, here, x and y, passing through the point P, passing through the point P. Then if you apply, maybe it is, maybe let's use the colors. So if you apply the second fundamental form to these, they are extended to the vector fields, of course. Then it's going to be perpendicular to both of those vectors. Okay. That's how this operation acts. Also, if the codimension is more than one, then it's not here. It's perpendicular, but not. It doesn't have to be the unique perpendicular lying on the unique perpendicular line. In general, you actually have more room to stay. All right. So taking its trace, taking it taking its trace is going to give you what we call the mean curvature vector field of the submanifold. Trace gives the mean, gives the maybe let's do it a little bit right in the lower piece. Taking its trace gives the mean curvature vector field. Mean curvature vector field of the submanifold. N. All right. All right. So it is like this time. So it is. Previously, it was a number, but here it became a. If you take the trace, it is going to be a vector field in general. Vector field in general. So that how are you going to compute it? Just plug in basis, orthonormal basis vectors of the submanifold. Is running from 1 to n of the submanifold. Orthonormal basis. For Tn, then you can compute this as the sum minus nabla ei plus nabla t ei, right? So I is running from 1 to n. All right, so our remark is that regardless of the codimension, this is vector field on n only. So it's not a vector field on the bigger space. It's only on n, and it's a vector field, and it's not a number as in the surfaces. All right. So for surfaces, let's make that remark to to provide the connection. For surfaces in R3, choosing an orientable orientation compatible. So there is a unique orientation compatible vector field. There is a for surface in R3. Let's put it that way. There is a unique orientation. Unique orientation compatible normal vector on N and mean curvature vector field is just the vector field is obtained by rescaling this unique normal vector field by a function so that mean curvature is a function which is a number at each point. All right, so curvature, so mean curvature turns out to be a number for surfaces in R3 because once you choose a normal vector, then the multiple of the normal vector is just a number, so that you can simplify to that number, which is a of course function on the surface. Function on the surface. So that also for hypersurfaces, you can think it as a function. Similarly, for hypersurfaces, you can think it as a function. I think Torf's differential geometry book is based on its exposition is based on hypersurfaces. That, for example, there you can think that as a function or a number at a point, mean curvature. But in general, if you have higher codimension, you should think in terms of vector field. Actually, the correct way to generalize it, generalize the mean curvature is a vector field. So the correct way to generalize so what we understand from these is correct Generalization of mean curvature for higher codimensions is to think it as a vector field on the submanifold as a normal vector field. Okay, it is normal also as a on the submanifold. Or you can say that it's the section of its normal bundle, right? So section of its normal bundle. All right, so that's the correct way of thinking about mean curvature in higher dimensions. I think so. We spent enough time on in introduction. So before doing the variation formulas, so that let me finish with the symbolic picture. Symbolic picture. So this is your small n lying in big M, and you have a mean curvature vector field along your submanifold. Okay, so that's your setting. So that's which is the trace of the second fundamental form, and in the next lectures we're going to see whether making it zero is going to be a good idea to define minimal submanifolds. Normal, unique. There is a unique orientation compatible normal unit normal vector here also, unit length, and then makes it unique. All right, so that was what we say about some motivations and basic notation about minimal surfaces. And in the next lectures, we're going to continue with making up minimal submanifold equations and looking at variation formulas. All right. So that's all for today. Any question? All right. Thanks for joining, and we will meet tomorrow.